Hello students, my name is Shashank Shekhar. Today we'll start hydrocarbons. So in starting from hydrocarbon, first we will see the preparation of alkane, then we will say physical properties of alkane and then the chemical properties of alkane. So if I talk about the preparation of alkane, so alkane can be are generally prepared from petroleum and natural gas. So they are the main sources of alkane, and how they are done means they are the main sources. Okay, so but the thing that is obtained is quite crude in nature. Okay, so they can be either unsaturated hydrocarbon also. So we have to synthesize it further. So if talking about the resources or talking about the compounds from which we will derive alkane are of three types. So first we will derive it from unsaturated hydrocarbon, then from alkyl halide, and then from carboxylic acid. So first from unsaturated hydrocarbon. So what is unsaturated hydrocarbon? If you remember, they are the hydrocarbon which contain carbon-carbon triple bond or carbon-carbon double bond. So they are termed as what? They are termed as they are termed as what? They are termed as unsaturated hydrocarbon. So what do we do with the hydrocarbon? With this hydrocarbon, we add hydrogens. Okay, we add hydrogens to them, and in the presence of catalysts like platinum, palladium, or palladium or nickel, and upon hydrogenation they form the alkane. So what do we see? But what do we do simply is we add the hydrogen here. If you see between this carbon and this carbon, you have a double bond here. So what do we do? We take platinum as the catalyst, which provides the surface for hydrogenation. We add hydrogen to it. Now this double bond is cleaved during a transition state, and two hydrogens are added on the either side, on this carbon and on this carbon. Similarly, if you take uh, another alkene, if you add hydrogen to it, again in the presence of any three catalysts. So you can take any either of the three catalysts like platinum, palladium, and nickel, and that will result in your required product, which is a alkane. So this is alkane. So we are getting alkane from alkane, alkene from alkane. Okay, we are getting alkane from alkene. Sorry, or we can do it for alkyne also. So we have taken an alkyne here. See, it is a CC triple bond. So upon hydrogenation in presence of platinum, palladium, and nickel, it gives us this alkane compound. Okay, so either you take this or you take this, you will get the same compound back. Now, what are the steps that are occurring during this reaction? First of all, the metal catalyst, okay, they provide a surface for the adsorption of the hydrogen molecule. Okay, so hydrogen molecule absorb here, and hydrogen bond is been cleaved during this process. Okay, this is the first thing. Now generating reactive hydrogen. So when the bond is cleaved, that will result in two hydrogen radical on the metal surface. Now the surface bonded hydrogen atom react with the unsaturated alkene and alkyne to add across the double bond. So wherever the double bond or triple bond is present, that also is also capable of forming a chelation type of thing with the say surface of the metal. Okay, because they have a pi bond. Okay, and pi bonds are more susceptible to interaction, so they interact with the metal surface and hence forms a temporary interaction. Now the surface has already the hydrogen reactive hydrogen radical, so it adds to the double bond, cleaving the double bond and forming alkane. Now in this whole process the metal plays a very crucial role by providing the surface for reaction, because hydrogen in its atomic state is very less reactive because it is in gaseous state first of all, and second thing, the bond is very strong. So by providing a surface for the adsorption of this hydrogen molecule or H2 molecule, we have a very stabilized transition state that is required for the reaction. Okay, so we have studied this. Okay, so we will study this also when we study chemical kinetics. We will study this about how this transition state is stabilized, but just for now consider that, okay, we have something, a transition state that is formed in between the reaction, and that is being stabilized by this metal surface. Okay, next preparation is from alkyl halide. So what do? We take alkyl halide, treat it with hydrogen in presence of Zn H+, okay, and that will give you simply CH4. Clear? Now this reaction is not for fluoride, so you cannot take alkyl fluorides and get your result, because chlorine fluorine bond is very strong and it is very short in nature, so it is very difficult to break that bond. For that reason, what do? We take only chlorides, bromides, and iodides, and then treat it with zinc in presence of H plus, and hydrogen is being added and HCl is being removed in this reaction. Okay, so here Zn and HCl are what? They are again Zn is doing the same thing, means the work of chelation that was being done by the metal, but in this case adsorption does not occur. Okay, adsorption does not occur, chelation occurs in normal, and this H plus is being facilitated to create HCl and all, and this CH3 converted into CH4. Next is Wood's reaction. So you will study Wood's reaction in class 12th also, so it is very important. So what do? We take a alkyl halide, we treat it with sodium metal in dry ethereal. Ethereal solution means that is free from moisture, to give higher alkanes. So whenever we take two alkyl halides and treat it with sodium metal in dry ethereal, then the alkyl part of the alkyl halide, suppose two molecules we have taken, so two molecules we have two alkyl parts, so they will both combine and form a longer alkyl chain, whereas the halide is given out. Now this reaction is Wood's reaction. It is used for the preparation of higher alkane containing an even number of carbon atom. Okay, so suppose we have taken an alkyl halide. Okay, so if we add two odd number, that would also result in even number. If you add two even number, that will also result in an even number. So from that perspective, so if you are taking a alkyl halide, so whether that alkyl halide contain even number of carbon or odd number of carbon, but since you are doubling it, it will always result in alkyl chain that will have an even number of carbon atom. Clear? Okay, so here is an example for you. So in the first case, we have taken odd number of carbon in the alkyl chain, which is CH3Br. Now they both carbon have had added and given a compound that is having even number of carbon. In the second case, we have taken even number of carbon in the alkyl halide. Again, it is also giving the even number of, means the alkane chain that is containing even number of carbon atom. Clear? So you can see the reaction condition. We have taken dry ether to keep it moisture free, because sodium is very reactive in nature. It reacts even with the free oxygen. Then hydrogen is just a, you can say it is just a good, very good reactive intermediate for that. Sorry, reactive part for that. So it will quickly catch fire even in water. Okay. So this reaction proceeds through a free radical mechanism and involves the formation of carbon-centered radical and their subsequent reaction. So this clearly goes by the radical mechanism. So if you have, suppose, so why this point is mentioned here? So this is very important. So whenever you have two alkyl halide, right? You have two alkyl halide. I mean that you have the same metal. Okay, you have the same compound, and there are two halides that are attached to the same compound. Means we have a dihalide compound simply. Now there are two possibilities. Okay, either you can go to one of them, first of the one. Okay, or it can go the second one. So you will attach the part from the alkyl part from where we have a stabilized radical. So this is for this reason it is mentioned here that the mechanism will go through a radical mechanism. Okay, radical pathway. Next is from carboxylic acid. So what is being done here? So in case of carboxylic acid, what is done is that we take a carboxylic acid and treat it with sodium hydroxide. Now that will result in carboxylate, okay, carboxylate ion, right? Now this carboxylate ion is when treated with calcium oxide in presence of heat, then it gets cleaved out. Okay, so you can see that this CO O minus is cleaved out and is now attached to Na, which results in Na2CO3. Okay, clear? So in this process, the process of elimination takes place, and the group which is being eliminated is COO, and that results in the formation of CH3, CH2, CH3, which is our propane. Okay, and the overall reaction is called decarboxylation. So this is a very, very important reaction. You will often encounter this reaction whenever you are dealing with a more complex reaction, right? Okay. Next is coal-based electrolytic method. So again, we are taking the sodium salt of carboxylic acid and we are hydrolyzing it. So it also goes through radical mechanism. Various parts of this compound are broken and converted into radical, and this radical combined with each other to give a numeral number of alkane. Now, since we have taken only one carbon apart from the carboxylic part, so that has resulted in one compound. If you would have taken, suppose, a longer chain here, then there will be more chances of cleavage, and that would result in a number of alkane that are possible. Now, this reaction of course follows a very complex mechanism, and it is believed to involve the formation of carboxyl radical as intermediates. As I have said, that they go through the radical mechanism, and it results in the formation of alkane at the anode. So this is very, very important. So we are doing electrolysis, right? So we have a anode, we have a cathode. So the alkane part, if you talk about this one, that is C2H5 that is formed, this product will be formed at the anode. So this is very important to remember. Okay. Now alkanes, we're talking about the physical properties. So most of the alkane are what? They are non-polar in nature because of the covalent character of carbon-carbon and carbon-hydrogen bond, and a very little electronegativity between carbon and hydrogen. Okay, so since there are no polar bonds that are present in this case of hydrocarbon, so that results in a very non-polar nature of the molecule. Now, this non-polar nature is responsible for the physical properties as well as the chemical properties of the alkane. Okay, so whether you talk about the physical properties and chemical properties, they are very much uh, less reactive. First, they are very less reactive. Second thing, they are less soluble. So many more properties will be explained in this way also, only where we will consider the polarity. Okay, clear? Now, since they have no polarity, but molecules have to be constituted in one place, right? So if it is liquid, then all the molecules should have some force of attraction that is holding them together. That is the reason they are forming liquid. If it was not the case, then they would have just shattered in the environment and resulted in a gaseous phase. So the force that is being acting here is the van der Waals force, and it depends totally upon the size of the alkane that we have. Okay, so greater is the van der Waals force, and that will result in much more higher interaction between the molecules. So we are talking here about the attraction between the molecules and not between the atoms and all. Right. So this should be kept in your mind. This is intermolecular interaction. Van der Waals force is the intermolecular interaction. But it is a weak force as compared to ionic force, covalent force. Okay, so electrostatic force, hydrogen bonding. Compared to all of this, van der Waals force is a weak force. Now, due to the weak force, the first four members of the hydrocarbon, starting from C1 to C4, or the alkane, I would say more specifically, the starting from C1 to C4 are gases. So, if you talk about CH4, C2H6, C3H8, and C4H10. Okay, so they all are what? They all are gases because of the weak van der Waals force that are present. But as the molecular mass increases, they become, can say, their element van der Waals force with the forces between the molecules, which is of course due to the size of the atom, size of the molecule, they increases. The van der Waals force increases, and hence from C5 to C17 we see liquids, and those containing carbon greater than 18. So if you have a hydrocarbon which is alkane and that contain 18 carbon atoms, then they will be solid at room temperature. Now, talking about their physical appearance, so they are colorless and odorless in nature. Now, there is a steady increase in boiling point with increase in molecular mass. So, we have seen that, okay, the interaction can be well versed with this state also. But it is again mentioned that, okay, that would again result in a higher boiling point. Now, this is due to the fact that intermolecular van der Waals force increases with increase of the molecular size or surface area. So it is mentioned here also. So if you are taking, first of all, the molecular mass is very important. This is the main deciding factor. Now, if two other compounds are having the same molecular mass but different structure, now you will see that are they more branched or they linear. So if they are more branched, that would result in a less surface area and hence less van der Waals force. Now, if they are linear, right? If they are linear, you take something as linear, then it will have a more surface area as compared to the branched one because they are not coagulated. So as we increase the branching, the molecules coagulate or come closer to each other, right? And that would result in a less surface area and hence less van der Waals force as compared to the linear one. Okay, clear? Next, here are some here's a table for you that will clear that how this van der Waals force is varying. So with the help of boiling point and melting point, you can clearly see it. See, as the molecular mass is increasing from methane, ethane, propane, butane to nonane, decane, icosane, you will see that the boiling point is also increasing. So we have 101 11 Kelvin, 184 Kelvin, 230 Kelvin, 272 Kelvin, going up to 423 Kelvin, 447 Kelvin, 615 Kelvin. Okay, so this is very, very important, right? Now, talking about the melting point, it is varying accordingly. Why it is varying? What is the reason behind it? And there is also still some variation in the say this one also. So here you can see that although they have the same formula, they have a different name, and hence we can see the variation in their boiling point. So what is the reason behind it? The reason behind it is the second factor, that is the surface area. So molecular mass is all the same for these three. See, these three have the similar molecular mass, but this one is a normal pentane, so it will have a linear chain. So if you convert it to 2-methyl butane, then it will have a branch chain. If you substitute it twice, that will result in an even more branch chain. And hence, as the branching is increasing, the boiling point is decreasing, and hence is the say you can see that this melting point is also decreasing. Okay, got it? Okay, but here is an exception for you, that although it should have a decrease for C5H12, but we see an increase for this. Clear? 2,2-dimethyl propane, there is a increase. So boiling point has been decreased, but the melting point has increased very abruptly. Okay, clear? Now talking about these two again, as the branches have increased from butane to 2,2-methyl propane, the boiling point has decreased, and so has the melting point. Now coming back to octane, nonane, decane, the trend is obvious. So next is, if you talk about the properties of say alkane. Okay, so if you talk about the properties of chemical properties of alkane, they are very much less inert in nature. They are very less reactive towards anything. So if you talk about acid, bases, oxidizing, reducing agent, towards each of them, they are very less reactive. Okay, because of their non-polar polarity in nature. Because each of the reaction is kind of derived only when there is an unsymmetrical distribution of electron. So that gives an opportunity for the upcoming reagent to attack. So if there is positive charge, a negative charge will attack. If there is a negative charge, a positive charge will attack. But since it is very non-polar in nature, therefore it results in a very less reactivity. Okay. So one or more hydrogen of alkane can be replaced by halogen. So first, the substitution reaction. What we do is we replace the hydrogen with alkane or nitro group and sulfonic group. Now this halogenation takes place at higher temperature. Suppose it takes place at 573 to 773 Kelvin, or in the presence of diffuse sunlight or UV rays. So this is simply called halogenation, in which what do? We just heat it at high temperature, or we just do the cleavage with the help of ultraviolet rays. Okay. Now next, lower alkanes do not go nitration and sulfonation reaction. These reactions, because they are very much less polar in nature, so that is the reason they are not reactive towards nitration and sulfonation reaction. This reaction, in which hydrogen atoms of alkanes are substituted with any other say group, then it is called as substitution reaction. So what are we doing here is that we are removing hydrogen and adding different groups like nitro group, halogen group, sulfonic acid group. Okay, so this is simply substitution. We are removing a group and substituting another group, and that is called as substitution reaction. Got it? So this is our reaction that we have, that we're talking about, the halogenation reaction. So we have methane that is reacting with chlorine, and in the presence of H nu, this results in the formation of what? This results in the formation of chloromethane. Now this reaction does not stop here. So if we treat our chloromethane further with again 1 mole of chlorine, then a dichloromethane will be formed. Again, if it will treat it with the sunlight, then it will result in a trichloromethane, and at last we have tetrachloromethane. So this is a consequent reaction. Okay, it is going consequently, and the reason is why. What is the reason behind it? The reason is the H nu that is being catalyzing this reaction. Clear? So here is a common name for you. This trichloromethane. This is called as chloroform. Right? This is called as chloroform. So what is the mechanism of the reaction? See, the mechanism of the reaction is very important. Each and every steps should be kept in your mind. So it should be there in your mind. So which step goes first? What happened this step? What happens in the other step? We will see those. Okay. So starting the reaction, we have Cl2 molecule. Now this Cl2 molecule, in the presence of H nu, they get homolyzed, or they undergo homolytic cleavage. Now what is the result of this homolytic cleavage? That results in Cl dot and Cl dot. Okay, so two Cl radicals. We get two Cl radicals. And why it is happening? Because carbon-carbon bond and carbon-hydrogen bond are very short, because they are much lower in the periodic table. So we have a short atomic radius and hence a shorter bond length. As compared to that, the chlorine-chlorine bond is very long, and that results in a easier exposure or easier cleavage of this bond. Got it? Okay. So that is the reason we have three options: CL bond, CC bond, CH bond, but the CL bond gets cleaved easily. Next is propagation. So we call this initial step as initiation, because this is the first step. This reaction is initiating the whole reaction. Next is the propagation. So in the propagation reaction, this chlorine radical, they attack the methane molecule, and the reaction is being carried forward by breaking the bond between carbon and hydrogen to form methyl free radical and the formation of HCl. So here is the reaction for you. So this CH4 is reacting with Cl dot, okay, and this Cl dot, what it does, this Cl dot cleaves another carbon hydrogen bond that results in a carbon radical and a HCl. So each of this step is having a homolytic cleavage. Okay, there is no evidence of heterolytic cleavage in this reaction, and this reaction is called as this step is called as propagation reaction, because that Cl radical that was formed in the initiation step, that is propagating this reaction further. Clear? Okay. So this results in CH3 radical and HCl. Now this CH3 radical again cleaves one Cl-Cl bond, and that results in CHCl, CH3Cl and Cl dot. Okay, clear? So, so the chlorine and methyl free radical generated from above step A and B, now they thereby set up a chemical chain of reaction. Okay, so they see now that it has become a chain. This CH3 is say CH3 radical that is formed is cleaving other Cl-Cl bond, and the Cl radical that is formed is cleaving CH4 bond. So they are catalyzing, or they are initiating each other, right? So this initiates a chain reaction. So this is the kind of propagation of the formation of what? Of the formation of the radical. Okay. Now again we have seen that there is a chance of the formation of CH2Cl. Okay, sorry, CH2Cl2. Okay, so there is a chance of formation of CH2Cl2, right? So this is the step that we have. So we have CH3Cl. This reacts with Cl dot, that results in CH2 dot Cl. Okay. Now this CH2 dot Cl again reacts with a chlorine atom. Okay. Now this radical takes up the chlorine, that results in CH2Cl2 and Cl radical. Okay. So here we have the formation of a dihalogenated compound. So this is dihalogenated compound because this CH3Cl that was initially formed is again being cleaved further to CH2Cl dot. Okay, CH2Cl dot, and which is again reacting with a chlorine molecule, that is resulting in CH2Cl2. Okay, last is the termination step. So what happens in the termination step? So if two radicals are reacting, okay, if two radicals are reacting, that gives us the what? That gives us the termination step. So just you must need to characterize the reaction. So you can be given a question, and I've seen a question earlier, and it can be asked that you have to say that which of the reaction is termination and which of the reaction is initiation and which of the reaction is propagation. So there is a way to identify it. So if your reaction, if your reactant side has only and only radical present. So if you see here on the reactant side, in all of this termination reaction, we have radical present. Then we say that this reaction is termination reaction. If there is one radical and one neutral species, then it is called as propagation reaction. If all the species on the reactant side are neutral species, I would not say neutral, are not radical, then I would say that it is an initiation step. So this trick should be in your mind. that what is which we will call the initiation step. If the reactant side has only normal molecule and no radical molecule, then we call that step as initiation step. If there is a radical and a normal molecule, then you will call them as what? Then you will call that step as propagation. And if both of the reactant are radical, then you will call that as termination step. Clear? Okay. Now, next is combustion reaction. So, what is combustion reaction? So, in combustion reaction, we simply react our alkane with oxygen. So, this is the most, I would say, this is the most reactive reaction that is given by the alkane. So, here what happens if you treat the methane with oxygen, then it undergoes combustion to release CO2 and H2O. And in this process, the heat is released. Therefore, it is written in the form of negative sign. So, see, del H combustion is having a value of minus 890 kilojoule per mole. Okay. Now, here is one more combustion reaction that you can have. It is C4H10 13 by 2O2, 4CO2, 5H2O. Now, this combustion reactions are important, and you must know how to balance them. Okay, so this is very important. So how do you balance them? So first of all, what you do is you balance carbon. Okay, you balance carbon. So if you just go back here, okay, here. So if you want to balance this reaction, first of all, balance the carbon. So 4 carbons are there, just multiply it by 4. So this carbon is balanced. Next, you try to balance the hydrogen. So 10 hydrogens are there, multiply it by 5. Then you will get 5H2O. 5H2O means 10 hydrogens. Now the thing that is left to balance is oxygen. So since there are 8 oxygens here and 13 oxygen here, and in this side we have only 2. So just what you do, just count the number of oxygen on the right hand side and divide it by 2 and then multiply this by this molecular oxygen, and then you will get the final combustion reaction. So this is a general formula for that. So whatever be the number of carbon, multiply it by that. Okay, whatever be the number of hydrogen, multiply H2O by that, and finally whatever be the number of oxygen, that is n in n plus n plus n plus 1. Okay, it is simply n plus n plus 1, right? But there are since 2 oxygen in this atom, this molecule, so 2n plus n plus 1, that will result in 3n plus 1 oxygen divided by 2. Multiply it by the molecular oxygen, and that will give the final equation. Okay, so this general reaction you should remember. Okay, now in the previous reaction we have a complete combustion. This reaction includes incomplete combustion. So what is incomplete combustion? First of all, so in incomplete combustion we supply partial oxygen, means not, I would not say partial oxygen, it will supply limited amount of oxygen, and that results in very uh, dangerous project. So why I'm saying it dangerous? Because incomplete combustion of carbon is very dangerous to the environment. It produces unfriendly, or you can say environment unfriendly products, which is very hazardous to us. So it includes carbon monoxide and all. So carbon dioxide is okay. Carbon dioxide is, although it is very harmful, but carbon monoxide is very much toxic in nature, right? So that is very harmful as compared to the carbon dioxide. So during incomplete combustion of alkane with insufficient oxygen of amount of air or dioxygen, carbon black is formed, which is used in the manufacture of ink, printer, printer ink, black pigment, and as filter. Next is controlled oxidation. What it is? It is controlled oxidation. So we are controlling the oxygen so as to produce the required product that we are looking for, right? So here we have CH4. Okay, we have CH4 which is reacting with O2, right? That is done in the presence of copper at 523 Kelvin and 100 atm pressure. Okay, which results in CH3OH, which is methanol. Similarly, if you treat that same molecule, that is methane with oxygen, but in the presence of a different catalyst like molybdenum oxide, then that will result in methanol. Okay, so it is giving us more oxidized product. Now, this is a kind of regulatory amount of oxygen supplied, dioxygen supplied to the methane, that results in different type of compound, and it is done at high pressure or at high temperature or at both. Next example, we have ethane here. So we are reacting it with oxygen. okay, in the presence of catalyst, which is a salt of acetic acid. Okay, so it's simply salt of acetic acid with manganese that results in ethanoic acid. Okay, next is what? Next is oxidation of reaction, oxidation of alkane. So we treat our methyl propane with KMnO4, which is a very strong oxidizing agent, and it converts your methyl propane to methyl propane to 2-methyl propane 2-ol. So here one OH is added. Okay, because since it is a tertiary carbon, it cannot oxidize it further into aldehyde or carboxylic acid, and that is the reason we are getting a normal alcohol here. Means it cannot cleave the bond. Okay, so this is very important. So whenever you have a say a tertiary carbon, you cannot do the oxidation behind alcohol. The reason is that you have to cleave the carbon-carbon bond, and that would require very harsh condition. Next is isomerism. So N-alkane on in heating in the presence of anhydrous aluminum hydride and hydrogen chloride, it gives us branched alkane. Okay, this reaction is very important, which is called as aromatization. Okay, so what do? We take hexane. Okay, we take hexane. We take a very high temperature. Here it is 773 Kelvin. So if you just think about it in degree Celsius, then it would be how much? So 273. So we'll subtract 273. We will get it as 500 degrees Celsius. So you can think of how high the temperature would be there. Okay. Now at very high pressure, so that its pressure is 10 to 20 at ATM pressure. So it is 10 to 20 times larger than the atmospheric pressure. Okay. And in the presence of molybdenum oxide or chromium oxide or vanadium oxide, you can take either of these three oxides, and then upon this conditions, the hexane cyclizes and gives us a aromatic ring. So this is called as aromatization or reforming. Got it? Okay. Now next. Next is reaction with steam. Okay. Next is reaction with steam. So methane react with steam at 1273 Kelvin in the presence of nickel catalyst to give carbon monoxide. So this is a very harmful gas. Carbon monoxide is a very harmful gas, and this process is used for the industrial preparation of dihydrogen gas. So what we do is we treat our methane with water in the presence of nickel catalyst and heat, and that gives us carbon monoxide and hydrogen. Next is pyrolysis. Okay. So in pyrolysis reaction, what do? We take higher alkene, and on heating it to higher temperature, this decomposes into lower alkane. Now you cannot predict the product here, okay, because it results in various fractions of the larger molecule, and that cannot be predicted merely with help of any generalization. Now such a decomposition reaction is used for the uh, application or preparation of a small molecule. Okay, now here we use cracking method. So this is called as cracking. So what are we doing? We are simply cracking a larger molecule into smaller pieces. So this cracking method is used in the refining of petroleum also. Okay, so where we crack this petroleum to get various products. So for similar to that we are doing. So it requires a very high temperature. Okay, and suppose we have taken hexane, so it can be converted into C6H12H2 or C4H8 or C2H6, C3H6, C2H4, CH4. So this type of products are possible. So I am saying that maybe your product can be this set or this set or this set. So it is probabilistic. Okay, it is probabilistic. So this is called as pyrolysis or cracking reaction. Next is pyrolysis of alkane is believed to be a free radical mechanism, and preparation of oil, gas, or petroleum from kerosene, oil, or petrol involves the principle of pyrolysis. So I've said it that to get various derivative of petroleum, we use this cracking or pyrolysis method, so which is believed to go through the radical mechanism. So for example, dodecane, which consists of 12 carbons, so if you heat it at 973 Kelvin, so it is how much? It is 700 degrees Celsius temperature. So in the presence of platinum, palladium, or nickel, then it will give you heptane, pentane, and other smaller products. So you cannot predict it at all that what a greater what a enormous number of smaller alkanes can be formed from here. So this was for today's lecture. So with this, I end my lecture. Thank you.